Hello everyone and welcome to this lecture on logistic regression. Logistic regression is a method for analyzing a data set in which there are one or more independent variables that determine an outcome. It is used extensively in various fields including machine learning, most commonly for binary classification problems. Logistic regression models the relationship between the dependent binary variable and one or more independent variables by estimating probabilities using a logistic function. Let's explore this further in this lecture. As a recap, so far we have discussed concepts like machine learning. We also discussed supervised machine learning and its two broader types, regression and classification. We also discussed regression technique called linear regression. We have also covered k nearest neighbor and decision tree algorithm for classification problems. We have also covered performance measures apart from classification accuracy and mean squared error. They are precision, recall, R square, and AUC score. The content of this week are as follows. In this week, we will cover the logistic regression algorithm. We will focus on artificial neural networks. We will also start discussing what do we mean by unsupervised learning. And within unsupervised learning, we will be focusing on the concept of clustering, and we will understand that with the help of algorithms. For the content of this lecture, we will discuss logistic regression. We will see an example and we will also look into the Python code to implement logistic regression. Let's start with the typical classification scenario. Here we have two independent variables and one dependent variable. It is classification because as an outcome, there are only two possible outcomes. Either the answer is going to be yes or it is going to be no. If you look at this data, however, the data here is nominal in nature, means the wind speed is given as numeric value, temperature is also a numeric value, but the corresponding class is a string, either yes or no. However, if we want to, we can convert that into numeric values as well. Here, we have taken an approach to move from classification to regression. That is, once you have converted the textual values of the dependent variable y into numeric values where y represents yes and 0 represents no, we have converted all the data into numeric form. Once done, we can in fact apply linear regression algorithm because our data has become all numeric by now. So here we have two independent variables and one dependent variable which is numeric in nature. That's why we can apply linear regression algorithm here. What we can do is we can follow the standard linear regression approach. That is, we will try to fit some curve fx on this data set of x1, x2 and y. We will get some value of fx for a specific value of x, where x represents the set of x1 and x2. Once we calculate this fx value which represents a curve, we will then check what is the value of that fx. If it is greater than 0.5, then we can predict a yes. Otherwise, we can predict a no represented by the value 0. Though we can follow this process, but this strategy is not very practical due to various reasons. Let's explore why this is the case. First of all, if we try to fit a curve fx with the help of linear regression algorithm, the output may not always lie in the range 0 and 1, which is typically the case for classification problems. The linear regression algorithm is very sensitive to data, especially the outliers. And finally, if we look at the nature of the data for classification and regression problem, they are very different in nature. For regression, our data usually looks like this. But for classification, our data looks like this, where for some x value, the corresponding class would be 0, and for rest of the values, the corresponding class would be 1. So even though by converting the textual data into numeric categories, we can actually apply linear regression algorithm, but it is not very practical. That's why it is avoided. Then comes logistic regression. In logistic regression, the primary objective is to restrict the values between 0 and 1. For that, we use a function called logistic function. A logistic function is given by this expression, 1 divided by 1 plus e to the power minus t, where t is represented at the horizontal axis, and the logistic value pt, which also represents the probability based on t, is represented using the vertical axis. This function has a very specific behavior. If we pass the value of t as 0, it gives us the value corresponding to 0.5. As the value of t moves into the positive direction, we will get the values greater than 0.5. And as the values of t moves toward minus infinity, the logistic function gives us values less than 0.5. Now this curve captures the behavior of the classification data we are having, where for some value the class is 0 and for some value the class is 1. So the logistic regression gives us a handle to always restrict the values between the range 0 and 1, where if the value is greater than 0.5, we can predict the corresponding class as 1 or yes, and if it is less than 0.5, then we can predict the class 0, which means no. To cover all the criteria, we also include equal to sign here as well. So in the case of logistic regression, we try to fit our data not only on fx but on this logistic function, where fx is one of the argument of this function. Here fx could be any curve, and it depends on the complexity of the data being trained on. If we compare logistic regression with the linear regression, the basic difference would be that in linear regression we try to fit a curve fx, but in logistic regression we try to fit the data on this expression where fx is an argument to that. Once again, to remind you that fx can be any curve. It could be a linear combination of one variable. It can also be a linear combination of multiple variables, and it might also contain the quadratic term. To derive a function like this with quadratic terms, we have to first convert our data into corresponding form, and then we can apply the logistic regression algorithm. Let's see the logistic regression algorithm. In it, first start by taking n examples as our training data set. Then we decide some curve fx with coefficients or weights represented as b. Let's say our function fxb is a linear combination of all the independent variables. We start with the initial value of bi's as 0. So the initial value of b0, b1 and b2 in this specific case are 0. We also take alpha. Alpha here represents the learning rate, which usually takes the value between 0.1 to 0.0001. In this specific case, you might consider a learning rate value of 0.01. And this is the main updation rule to change the values of bi's. Bi is equal to bi minus alpha times the summation of this whole expression divided by n. It is important to note here that here I represents the number of coefficients. In our specific case, I start from 0 to 2, and j represents the number of examples which vary between 1 to n. Here the logistic function fxj, b can be calculated like this. To better understand this algorithm, let's take one example. Let's take this example. We have two independent variables, x1 and x2, and we have the corresponding value of y with two classes 0 and 1. Let's say we want to fit a curve fx, b, which is the linear combination of all the independent variables, including one constant term or bias term b0. Since b1 has the multiplier x1, b2 has the multiplier x2, we do not have any multiplier of b0. That's why we have written over here 1 as the multiplier of b0. This one will come into picture very soon. Now, as the next step, we have set the initial values of bi's to 0. As the other steps of the algorithm, we have taken the alpha value as 0.01, and as you can see in our data, there are 4 examples in total. So the n value is 4. Now, if we calculate the logistic value corresponding to this row, it is going to be 0.5. How it came out? If we put x1 as 2 and x2 as 1 in our expression, then fx, b will become 1 times b0 plus 2 times b1, because x1 is 2, plus 1 times b2. Now, since initially b0, b1 and b2, all of them are 0, then this expression will give us the value 0. And when we will pass This fx being 0 in the logistic function, by the characteristic of it, it will give you the value 0.5. So even though the values of x1 and x2 are different, the corresponding logistic value right now would be 0.5 for all of them, because all the BIs are 0 currently. Then we will calculate this expression logistic value minus y, where y represents the actual class value. So in first case, the expression became logistic value from here for the first row is 0.5. The actual value is 0 minus 0. So the answer is 0.5. The same is for the second example also. For the third case, when we take its logistic value 0.5 minus the corresponding class value y, which is 1, then the answer would be minus 0.5, and same is true for the last example as well. So in this way, we have calculated this expression logistic value minus y. Now let's start updating BIs one by one. So we have already calculated the logistic minus y values for each of the example. To update B naught, we will use the existing formula. B naught is equal to B naught minus alpha times the summation divided by the total number of examples. Here, once we have calculated this expression, we will multiply that with the multiplier of B naught, because right now we are calculating B naught. So if we follow our function, the multiplier of B naught is 1 here. That's why we will multiply this expression with 1 for each of the examples. As you know, multiplying with 1 will not make any difference, so values will remain same. And finally, we will calculate the sum of all of them, which turns out to be 0. So we will update B naught like B naught minus alpha value, which is 0.01, times the summation, which is 0, divided by the total number of examples, which is 4. So B naught became the previous value of B naught, which was 0. So B naught will not change and its value will remain as it is. Let's try to do the same process for B1 also. When we want to update B1, then this time we will multiply the logistic value with the corresponding multiplier. We know that the multiplier of B1 is x1. So we will take this expression, multiply with the corresponding x1 value, which is 2. So the answer is going to be 1. In the next iteration, once again we will take the logistic value, we will multiply that with the corresponding x1 value. The answer would be 1.5. The same process we do for rest of the rows also. When we do it and calculate the sum, it turns out to be 1. So we will update B1 as its previous value minus alpha value, multiply with the sum divided by 4. This expression will give us value 0.0025. So as you can see, B1 has now changed from the value 0. Similar process we will do for B2 also. The only difference would be that this expression will be multiplied with the multiplier of B2, the multiplier of B2 is x2. So we will multiply 0.5 with the corresponding x2 value. So the answer would be 0.5. In this specific case, the value of logistic with the corresponding value of x2. So the answer would be minus 2.5 and so on. Once we have calculated all these values, we will calculate the final sum, which turns out to be minus 4. And when we put it here, the updated value of B2 is going to be 0.01. So this is only the first iteration of logistic regression. Since the value of BIs are changed now, this time when we once again calculate the logistic value for each of these examples, the value will differ from 0.5. Now we have a different set of values. We will continue with the same process again and again for a number of maximum iterations. When we do it enough times, we realize that after certain number of iterations, the values of BIs are not changing and they have reached to a saturation point. It turns out the value of B0 turns out to be minus 0.0969. For B1 it is minus 0.38 and for B2 is the value is 0.39. So once their values are not changing anymore, we will stop at that point. These are the corresponding coefficients of the curve fxb. So our fxb turns out to be this expression B0, B1 and B2. Now, if we plot our data, then 2, 1 comes here, 3, 2 is this point, this is 1, 5 and this is 2, 6. If we take our fxb and put it to 0, then actually we can write x2 in terms of x1. If we pay attention closely, it is similar to the line, the equation of a line. So this fxb actually in this specific case gives us a line. If we plot this line, then this is our fx is equal to 0. It is called a decision boundary. We have seen this concept in the earlier lectures also. A decision boundary is a curve which separates one type of examples with the other type of examples. In this specific case, whenever fx is greater than 0, it represents the region of class 1, and whenever fx is less than 0, it gives us the region of class 0. That's why fx is called a decision boundary, which separates one type of examples with the other type of examples. So a decision boundary is a curve which separates positive examples with the negative examples. To do the further reasoning, to identify the class of a new instance, this is what we can do. We will put the value of that new instances into our function. If it turns out to be 0, which also means that the logistic value is 0.5. If it is greater than 0, which also means that the logistic value is greater than 0.5, and it corresponds usually to class 1. And when the value of fxb is less than 0, it corresponds to the class 0 and the corresponding logistic value is less than 0.5. It is important to note here that 0.5 is called a threshold value. Often 0.5 is taken as threshold, but a different threshold can also be considered. The choice of threshold depends on the specific goals and requirements of your problem. If we can tolerate missing some positive cases, a higher threshold like 0.7 may be appropriate. However, it's essential to consider the consequences of the threshold choice in the context of the specific application. Since we are raising the threshold, it means fewer instances will be classified as positive class. This means that the model may generate fewer positive predictions overall. It can be a desirable outcome in certain applications where we want to be cautious about making positive predictions. I'm mentioning it here to let you know that there are situations where we can change the threshold values. But otherwise, the most common usage of threshold value is 0.5. So what is the next step? Like other algorithms we have seen earlier, the next step includes testing this specific model on unseen test set. And if the performance is not satisfactory, we can try using different curves and different combinations of independent variables. What about unseen instances? How we can predict their classes? Let's say for an unseen instance, the value of x1 is p and the value of x2 is r, and we want to know what is the corresponding y value, either it is 0 or it is 1. So what we will do is we will put the value p in this expression and r also, and by now we already know the value of bi's, in this case b0, b1 and b2. We will calculate the corresponding fxb and then we will pass it to the logistic function. If the logistic function gives us value greater than or equal to 0.5, then we will predict the corresponding class as well, and if it is less than 0.5, then we will predict the class 0. Once again, remember that here we are considering the threshold as 0.5, but we can vary this threshold as well. So all this region where fx is negative, the corresponding class would be 0, and all this region where fx is positive, the corresponding class would be 1. To summarize, in this lecture, we focused on the algorithm logistic regression, and we also discussed what do we mean by decision boundary and how logistic regression creates a boundary. Now we will see the implementation of logistic regression in Python. Thank you. Welcome to the implementation of logistic regression. Let's see how we can use logistic regression algorithm using inbuilt libraries. As you can see on your screen, I have already mounted my Google Drive. Let's import necessary libraries in order to implement logistic regression. The rest of the libraries I hope you are already familiar with. We have train, test, split functionality. We have accuracy score, and then we have this logistic regression function also. Let's run this. Now we will load the data. It is the same iris data set that we are using right now. Let's see the head of the data and shape. So I have taken the iris data set, but right now I am considering only 2 classes, not the 3 classes. Original iris data set has 3 classes with 50 each. So it has the overall size of 150 rows, but currently I am using only 2 class data, so we have only 100 instances. We are doing that because originally logistic regression was developed for binary classification problems. That is, it can handle only 2 classes. Let's see the species count for both the classes. So we have these 2 classes available. One is Setosa with 50 instances and versicolor with 50 instances. As you can see in the original data set, the column ID is extra, so we will drop this column. So after dropping, we have only 5 columns left. 4 are independent, 1 is dependent variable. Once again, the column species here contains string values, character values. However, logistic regression requires that to be converted into some numeric representations. For that, as we have done earlier, we are using the label encoder. So using label encoding, we have converted the textual column into the corresponding numerical values. So one class is represented with 0, that is Setosa, and versicolor is represented with the value 1. Now we will draw the original species column that contains the textual information, and will keep only the encoded species column as our dependent variable. Once again, we will remove the dependent variable column species encoded from the X data, the matrix of independent variables, and we will keep it as the column vector, which is the dependent variable Y. We will once again do the 90%, 10% train and test split. Let's see the size of both training dataset and testing dataset. It is 90 for training and 10 for testing. Now create a logistic regression classifier and fit on our training dataset. Now once we have done that, the next step includes predicting the performance on the training dataset and check its accuracy. When we run this, it turns out that its accuracy is 1.0, which represents 100% accuracy on training dataset. Let's do the same for testing dataset as well. This time when we run on testing dataset also, the corresponding accuracy is 100%. So in this way, you can use the logistic regression classifier very easily for binary classification problems. In the next lecture, we will focus on artificial neural networks. Thank you.